Welcome to this Think Small Cell webinar. Our topic today is laying the foundations for phase timing, and our guest presenter is Eric Colard, Head of Emerging Line of Business at Microsemi. The format today will be that Eric will give a presentation followed by a question and answer session. And at any time during his presentation, feel free to submit questions using the control panel on your right. The slides and a recording of the event will be made available within 24 hours. So without further ado, I'd like to hand over to Eric for his presentation. Eric.
Yep. Thank you, David. So thank you everyone for joining. I'm going to go over a presentation that's focused on phase, timing, requirements, and challenges for operators. And as part of that, I'll give you also an update on how we at Microsemi are solving these phase requirements problems. All right, so what we've been seeing, Microsemi is a very prevalent, leader in the phase and timing synchronization space. We have a lot of deployments out there, and what we've been saying in the past, several months is a move from frequency, timing, and synchronization to phase. We've seen it, in many areas of the world. Initially, the North America market, and then the leading, Asian countries such as Japan, Korea, China, and Taiwan. But now we're seeing that move across the board in many areas of the world. So phase and time, is basically being driven by migration, from solid SDH to a very, stable frequency first, with SYNC and optical transport network. But what is really driving the phase requirement is the move from LTE to LTE advanced type of capabilities that we'll go over more, in details in this presentation. And also, deployments that are emerging in the small cell arena. I mean, of course, 5G is a few years away with 2020 type of deployment date targets, but we're seeing a lot of distributed architecture, in terms of mobile networks, more and more flavors of base stations that need to be cognizant, basically, of the requirements to avoid interference and the coordination between the small cells and the macro cells. And all of those lead to phase being a strong requirement nowadays in the mobile networks. So just a reminder of the requirements from an ITU point of view in terms of the capabilities and the performance. So frequency, 50 ppb in terms of intercell alignment has been around for a long time as a requirement. Early on with the GSM networks, it's still the same requirement for even LTE for the frequency flavor FDD. In terms of time and especially the phase requirement, you probably know that the standards, point to plus or minus 1.5 microsecond for phase. What I want to point out here is that phase is not only required for TDD, the flavor of it, LTE, TDD, but it's also the case for FDD deployments when LTE advanced type of services are being deployed and considered, mainly for interference mitigation and some applications that require strong phase, like video services, eNodeBs-not or NBSFN, and the deployments of comp type of networks as well. So as soon as you have intercell phase, sync alignment, or coordination between macro cells and small cells, or between the small cells together, then you would require phase. So it's not only for TDD, and that's a major clarification I wanted to point out here. So in the next few slides, I'm going to go over some of the vocabulary that is very important to keep in mind, when you consider phase. First of all, in terms of source, so the source of, in terms of frequency source, the element that provides that source and that reference is called the primary reference clock that many of you are very familiar with, PRC. And that is coming from either a GPS signal fed into a master or with a cesium clock. And you're probably well aware that Microsemi is a prominent vendor of that type of technology. So that's the, kind of the PRC product that has been very prevalent in networks, with Sonnet SDH and frequency type of deployment. What has been introduced in the last few years in regards to phase is the PRTC, concept, which is the primary reference time clock. So, and for the PRTC, the reference is coming from GNSS, and GNSS being, GPS and all the other constellations in other countries as well. It's very important to note that a PRTC needs to be traceable to universal time, UTC. So to keep in mind, for time, there's a new concept, which is PRTC instead of PRT. Now, another, element that, is very important to keep in mind when you talk about phase is actually the time error budget. A lot of people focus on the master, and we provide master products and, the capabilities and the performance and the requirements, the carrier grade, type of elements of the master itself. But when you consider phase, it's really about network engineering from the master to the consumer of phase and time. So basically from the PRTC to the eNodeB, that whole chain of elements and hops and transport network has to be considered. And to meet the 1.5 microsecond traceable to UTC, each of the elements of that chain has been assigned by the ITU a budget for time error. So for example, the PRTC itself, plus or minus 100 nanoseconds. The consumer of time at the end of the chain, the eNodeB, plus or minus 400 nanoseconds. And in between, you have 1 microsecond or 1000 nanoseconds for the network itself, the transport of time. And that's a major consideration that we'll go over more details in the next few slides. The number of hops and the issues that are related to the transport itself is a major consumer of that time error budget. And that needs to be really taken into account when deploying, the network for phase. And there's a lot of engineering of the network that needs to be taken into consideration. So it's not only, buying a PRTC and a master and having the right, a base station with the right client support for 1588, for example. What happens with the transport itself is a major consideration. So from a standard point of view, you may be familiar with the ITU-T work, and J.8275.1 is the first ratified standard for defining the time error budget in a full on-path support mode. So if you can see here, the details of the transport piece, which we highlighted in the slide prior at 1 microsecond, the total for the transport consumption of the time error budget. The two considerations that need to be highlighted here are the dynamic time error, introduced by the network elements and the links, and the network asymmetry. You probably know that on an optical network, for example, the downlink and the uplink may not have the same length. We've seen many deployments where the fiber, for example, to go from A to B has a very different length of fiber to go from B to A. and that introduces a lot of asymmetry that needs to be corrected. And so it's very important to not only take into account the number of hops that you may have in your network, the type of network elements that you may have in your network, and the ITU defines, up to 10 time boundary clocks, in the network to assist between the master and the slave. But if you don't take into consideration the dynamic time error and especially the network asymmetry, then you may have trouble, meeting the 1.5 microsecond. So it's very important to take these into account. So the second aspect is an OPEX, CAPEX type of situation related to the J.8275.1 time profile, which is also called the full on-path support. And full on-path support really means that every node between the grandmaster and the time slave clock needs to be equipped with a time boundary clock. So a time boundary clock may not be in your elements in your existing network. So you may have to either purchase a new network element that supports time boundary clock, or you may need to upgrade. But at the end of the day, you need to have every single hop, not some of them, but every single hop be upgraded or equipped with a time boundary clock. So it's a major investment that some carriers may need to be involved in. So carriers that are more, greenfield type of operators, which are not that many, but probably more in the emerging space, may just need to buy, network elements with boundary clocks, and the new network elements most of the time have those, but it's an investment. But for brownfield type of deployments, most of the advanced countries that have had a network, with packets and internet for some time, will have to upgrade, these existing network elements to support time boundary clocks. So that's a major issue that operators have been relaying as part of that time profile. So that requires as well a lot of engineering of the network to deal with what we discussed before, which is, the asymmetry. A lot of operators that have been involved are reluctant to deploy this type of profile. And those who have done that, for example, in Asia, a few operators have done that, have had to manually calibrate each of the link between the boundary clocks to take into account the uplink versus downlink asymmetry. So that manual involvement is very time consuming, very costly. So to be avoided in many cases. So the alternative to this full on-path support is the newly consented standard, which is J.8275.2. And J.8275.2 is partial on-path support. So on the diagram here on the network, instead of a boundary clock or a time boundary clock at every hop on the network, that type of boundary clock or assistant is placed at some very effective points and only at those selected points on the transport path. The second big difference that I wanted to point out here is that 75.2 is unicast layer 3 versus 75.1, which was presented on the prior slide, is multicast layer 2. So a lot of operators have deployed networks with layer 3. So deploying 8275.1 on that type of environment might be a challenge. So time error budget is a very key, consideration for deploying time and phase. In particular, operators have to look at, what is the time error that is associated with packets going across the network. The dynamic time error portion, plus or minus 250 nanoseconds, introduced by, packet buffering delays, and the switching network elements in the path, is one consideration. But the major consideration is asymmetry, and asymmetry is something that can be dealt with, and Microsemi has solutions for that. So, very important to know that boundary clocks don't solve the asymmetry. Boundary clocks is basically a network node with a master and a client regenerating the 1588 traffic at the node level. So the boundary clock doesn't solve whatever issues are occurring between the nodes on the link themselves. So manually calibrating each link is a major issue. So what we propose as a company is really to offer asymmetry compensation technologies that we have in several lines of products that we offer, that basically leverages the GPS signal at the masters, in the network, and enable basically to compare, two masters with GPS phase enabled, and use that information for when the GPS signal goes down. For example, you can actually assess what was the link asymmetry of that particular link between the nodes, because you have the comparison with another master equipped with GPS in the network. So you can manage asymmetry, you can compensate it automatically that way. And the second aspect that we want to promote in terms of architecture and network engineering is to place the master and the PRTC as close as possible to the eNodeB. So the combination of placing the masters closer to the clusters and closer to the eNodeB and the asymmetry correction, we think is the best approach to deliver phase to the very edge of the network. So what have we done actually in terms of recent announcements to actually deal with these types of phase deployments, and how have we adapted to the market to deliver those? So you may remember that a year ago, about this time of year, we had announced the IGM integrated GNSS master for indoor deployments. So that's a unit, a grandmaster with 1588 with a GPS, GNSS antenna, and a GNSS receiver, all bundled into one small form factor, with the goal of lowering the cost of deployment for small cells and the timing of small cells indoor. What we've done this year at the Mobile World Congress is to actually expand that family of products based on that same architecture of IGM to deliver 3 products. An IGM indoor, which we have provided some enhancements to, so I'm going to go over those. I'm going to go over some of the use cases that we have encountered when working with operators with the indoor version. Then the new products, an outdoor version of IGM for scenarios where either the indoor version cannot work. There are some buildings that can be challenging, so we needed an outdoor version for it. But there are also other use cases for the outdoor version that I'm going to go over in the next few slides as well. And then a version of the IGM that doesn't bundle or integrate an antenna inside the box for scenarios where the deployment of a GPS antenna is not an issue. So for example, if it already exists, if the GPS antenna and cable already is in the building, that deployment cost is not an issue. So that's one scenario. Or if the GPS cable has to be short, for example, if it's a cabinet and you install that mini grandmaster inside the cabinet, the connection to a patch antenna, for example, with a small cable is not a deployment cost issue. So for that type of situation, we have what we call the IGM 1100X to connect to an external antenna. So just a recap regarding the indoor version. The usual scenario is to have an a master deployed at the server room, connected to a GPS antenna on the roof to be able to deliver phase and to be able to deliver phase to the small cell deployed indoor in an enterprise. That was the premise of the original product. I won't spend too much time on it because we had a webinar. It's still available on YouTube on that product. So just a recap on why we actually did that product. On the top of the slide, you see a traditional Grandmaster. It's actually one of our Grandmasters, TP2700, with a cable that needs to go through the building and a GPS antenna on the roof. And you see kind of the costs, that are associated to that. The GNSS kit to buy the antenna, the cabling, and also the CapEx and OpEx from installation to rental of space on the roof, for example, that can be in thousands to tens of thousands of dollars. This is compared to the new way, innovative way of actually integrating everything and making the master an indoor product with capabilities to receive GPS, GNSS signals indoor. So no outdoor antenna anymore, no cabling of GNSS cable anymore, and simple installation that a person who doesn't know timing can do with auto configuration as easy as a Wi-Fi access point. So that's what we brought last year to the market. We've done some enhancements to that product that I'm going to go over in the next slide. So these are the enhancements in this new version of the IGM Indoor. So we have increased the number of clients. Last year, the base version is 4. There's a license to go from 4 to 8 clients. And in this new version, there's a license to now go from 8 to 16. We still think, that the setup for last year in terms of client support is the right setup for indoor enterprise. But this product has also been considered and trialed and has value for other scenarios than the indoor enterprise scenario. And so for those scenarios, there was a requirement to support more clients. So we have a direction to support more clients over time. So 16 is the version that we have today. Because we deploy now in other environments than just enterprise, there may be indoor situations feeding clusters of eNodeBs, for example, from an operator environment. And for those, there may not be an auto configuration server for small cells because there may not be enterprise small cells in the environment. So what we decided to do is to provide more management options. So today, we can provide an auto configuration server with TR69. We can also manage with CLI over SSH for ease of for security. We have also 2 antennas now mounted in the same box. So there's no need to have a wall or a ceiling version. The same unit deployed either way. So that's a change that we made from a hardware point of view. And then we added more capabilities in terms of sync. We now have syncly support in the product. And we also provided 2 legacy profiles for 1588. We support J.8275.1, and in the next few months, we'll support 75.2. But there are some base stations out there that support older profiles. So we needed to interrupt with those, and we have added Telecom 2008 and also the default profile to the product. So just a few pictures to highlight, the type of deployments or field trials that we've been engaged in with the product. So you see the unit on the bottom left of this picture, just to show, the type of flexibility you have with this product to deploy anywhere. It can be deployed like on the right side in an office, with a window view, but it can also be deployed, kind of a hangar type of situation like we see on the bottom left. This is, I wanted to give you also an update on what we think, what we experienced actually as compared to the initial thinking about the product. So initially for the indoor, we thought that it would work in about 80% of the cases, and that about 20% would be very challenging because of materials, because of no windows, metal cages, these types of issues. What we have experienced actually, and this is a picture of one example of that, is that the product actually works in many more environments than we initially thought. So this is, for example, an environment of a moving, mobile cabinet made of metal, as you can see, and there's no windows. There's only a door, and we've made testing. It works great either way, with the door open or the door closed. Obviously, with the door open, there are more, available and usable satellites to use. But even with the door closed, we managed to have the product work in such an environment with no windows and a metal cage. So we realized over time that 80% is probably a low number. We're much more than many more scenarios than we initially thought work with the indoor version. This is a couple of other examples. So on the top, you have a hotel. We had the product work in this hotel in Spain at the lower level, below the ground floor, sub-ground floor, level -1, in a conference room, no windows. And we thought it'd be a challenge, but it actually worked and didn't even require assisted GNSS signals to be used. So the net of that is it's very difficult to predict when it doesn't work, because scenarios where you would think are very challenging sometimes happen to be a good working scenario. So I would suggest not to give up. When people have a use case and may think, oh, that's not going to work in that particular scenario, I would suggest to try it, because walls sometimes actually let signals go through better than windows. So you may be surprised. But I want to be open, I want to be credible as well. On the prior slide, I was showing the Gherkin building in London. That's an example where we found challenges, because there are plenty of windows in that building, but we found challenges to make it work. So there are some scenarios where there's a challenge to make the indoor product work. So that's why we actually came up with the outdoor version of IGM, which I show on the top of the building. So it's for those scenarios where you serve indoor small cells, but like in the Gherkin building, it has challenges. So you just put the product on top of the roof. To make it clear, this is a combination integrated master and antenna together in the same product. So you don't have a master somewhere in the building, it's in the antenna itself, it's outdoor. And what comes out of that unit is an Ethernet cable. It's not a GPS cable. So even though it doesn't have the same, I don't know why the slides are moving, but even though it doesn't have the same value prop in terms of CapEx, OpEx savings as the indoor version, it still have a lot of capabilities that are very interesting and valuable. So the integration of the two products together in the antenna is a plus on the roof. The cabling, you don't need to have a GNSS cable go through your building either, because it's all Ethernet. So that's a major plus as well. It's common software, so the software you use for the indoor is also the same for the outdoor. The outdoor doesn't need a GNSS, assisted GNSS, so it doesn't need the ephemeris data to come from the network. It gets the ephemeris data from the satellites directly. So that is a plus as well. So you don't need to have a connection to that type of service. Just wanted to mention the operating range, -40 to +70, and it's still PoE and plug and play. Okay, so I'm not going to go over the details of the PoE deployment guidelines, but we have definitely, PoE products as part of Microsemi. There are guidelines on how you connect, an external antenna to, for example, an indoor PoE one-port unit like we show on the left side. You need, surge protectors like we show on the left side as well. And there are ways to, connect those. So if you need more information, that's on the slide. And this next slide as well is another way of deploying the antenna with a PoE midspan that is actually outdoor. So we have versions of the PoE that is a switch PoE for outdoor use that has 2 or 4 ports. And we show also guidelines on how to connect that to the antenna and to the rest of the network in terms of surge protection. So that's something to take into consideration. We have these products to complement the IGM. So this is another illustration of a use case for the outdoor version. This is not for small cells. This is not for enterprise. It's for a cabinet situation. Cabinet, for example, feeding and delivering phase to small cells or eNodeBs on the right side. So let's assume the cabinet has no space, which is, the case in many situations. You don't have the space to put either the pizza box, Grandmaster, or another type of Grandmaster. In that situation, you just put the Grandmaster in the antenna outside. You put it on the pole, for example, to avoid vandalism, and you connect the Ethernet cable to the cabinet, and off you go. You have phase delivered to the small cell. So that's a very convenient, flexible way of providing precise timing to small cells by not interfering with what the cabinet situation may be. So that's one of the use cases for this outdoor version. If the cabinet has actually air conditioning and has space and looks like a little bit like what I show here, then that's the use case for the 1100X version, for the external antenna. So it's basically a mini Grandmaster. It has the same software as the indoor and outdoor, so it supports up to 16 clients. It has the same PTP profiles than the other ones. It can be managed with CLI, for example, and it sends SNMP traps to the time picture that may already be deployed, in the environment to manage the other synchronization products in the network. So you can see on the left side, you can have a very simple, short cable to some type of L1 or patch antenna that could be, for example, on top of the cabinet. So, or if it's in a rack situation in an office, that's the type of product you could deploy as well. So a lot of flexibility on how to use this product, and it complements, the indoor version and the outdoor version by having a very low cost, cost-efficient mini Grandmaster for these types of deployments. So in terms of management, as I described before, we have several options. So the first one is an auto configuration server. We support PR69. We have a demo version that comes with the product that we've used for trial, but we'll use a commercial version for deployment. That's the first, option. This is really meant for indoor enterprise small cells because most of the small cells have auto configuration server capabilities as well to facilitate the deployment. So we want to mimic kind of the deployment model of small cells indoor for this timing device. For situations like I showed, either a rack or a cabinet or these types of scenarios feeding a cluster of eNodeBs, for example, then the CLI option is the one we offer over SSH v2 for security. So we have limited capabilities for CLI right now, but we are enhancing that, and we'll have a version that is very similar to all the other CLI support products that we have today so very consistent across all the product lines for packet time. And then we have SNMP traps to the time picture. The time picture is our management platform for sync that we use end-to-end from the SSUs down to this IGM at the very edge. And we'll have TP10 and ACS integration is on the roadmap. So in terms of are these products available, what is the timeline? So we actually launched the product at the Mobile World Congress in February. Right now, in March, we are at the very latest stages, of the pilot for both the indoor universal product and the mini GM for external antenna. So we are just in the process of releasing, and the general release is next month towards the end of April. So both the indoor and the mini GM versions will be available then as GA products. The outdoor version will follow in the next few months. The pilot is going to be end of May, early June, and the release is going to be in July for that outdoor IGM. So by July timeframe, we'll have the three options. So an operator can, basically has a portfolio at disposal to serve, phase and precise time at the very edge of the network with these three form factors, depending on the use case that is being considered. And from a pricing point of view, we have priced the indoor universal and the outdoor. After a certain volume, these two products have the same list price. So we want to make it easy for the operators, depending on the use cases, they can, plan without having to know exactly, do I need to deploy on the ceiling, on the wall, indoor or outdoor? I want to make it easy from that point of view. So it's a very similar pricing for these two products. And the mini GM is a more attractive product because it doesn't have antennas inside. So that's kind of the summary of this presentation, that initially focused on making sure we all align on what phase timing, challenges are out there for operators. Many operators are starting to deploy LTE advanced features, and phase timing is very essential. And there's a lot of thinking to be done in terms of network engineering for, time, especially the PRTC consideration, that new version of source of time, and also the considerations that need to be taken in terms of the transport network and the impact of the transport, the number of hubs, the investments in terms of boundary clocks that need to occur in some deployment models, and taking into account the network, the asymmetry. So we offer, solutions for that to automatically, deal with asymmetry correction instead of doing calibration link by link in a manual fashion, and to deal also with precise phase by providing masters that can be deployed as close as possible to the edge to serve small cells in a very precise fashion and a cost-effective way. So just mention that we were also finalists at the Small Cell Forum and also the LTE Award with the IGM Indoor in June last year. So I think we have some time for questions, David.
Yes, thanks very much, Eric. And I'm sure the audience would agree with me that you're very much a subject matter expert on this topic. And that was a very thorough review of both what the practical problems are and how Microsemi have dealt with them. We've got a few questions been submitted already, and feel free to submit more during this Q&A session. The first one I have is just going back to your earlier discussion. Could you clarify what the difference is between boundary clock and transparent clock?
Yeah, so a transparent clock basically is a device that has the ability to correct for the delay that is introduced by the network, by the node, by introducing a correction field inside the PTP packet. So you have a PTP packet that goes through, and there's a correction field in that packet that you can set to a certain value to take into account for the delay in that node. So it's just a field in that PTP packet for the correction. The boundary clock, on the other hand, is a node that has both what could be considered a master at the input and a client on the output. So it receives a 1588 packet, regenerates the 1588 packet with the master, and the slave that is in the same node puts out that packet to the next hop. So it's a different architecture, it's a different implementation. So it's only a correction field for the transparent clock and a master-slave combination in the node for the boundary clock. But both, from that point of view, deal with what happens in the node itself and try to correct with that node, but cannot correct what is going on in the links between the nodes and the asymmetry that is occurring between the nodes. So you've had deployments out there in the world, a few, with J8275.1 that was deployed with sync key for very stable frequency and a boundary clock at every hop for each of the node, but still had to go through a very tedious and time-consuming calibration of every node of the fiber optics between the boundary clocks. So it needs to be very clear that dealing with the nodes is not sufficient. You need to deal with the links as well and the asymmetry that is introduced by the network.
Okay, here's a very quick question. Should get a quick answer. How many clients can connect to the IGM box?
Yeah, so the base, the maximum right now is 16. The base version is 4, and then you can upgrade with the license to 8 and 16 with this version.
Right.
Yep.
And another product-related question, can the IGM receive or accept these PTP packets from an external grandmaster, or does it generate the PTP timing packets only from the GNSS source?
So in the current release, the one I presented today, we rely on the GNSS signal to generate the PTP packet from the IGM. But we are actually working towards a version, a revision of the software. So I can talk about it now because it's coming out very shortly, that will accept PTP input. So that's one of the enhancements that's coming for the July timeframe. So we'll support that. We definitely believe that it's critical to be able to receive PTP input from other nodes in case GPS has some issues. And we know that GPS or GNSS sometimes go down. And so there's a strong, architecture to rely on other nodes in the network is something that we would recommend. So yes, we will provide that in the next few weeks.
So a question from me this time. I've seen that many small cell vendors state that their products already include phase synchronization and cater for adapting inputs from GNSS, from the PTP, and potentially even sniffing external outdoor macro cells. Why would they need an IGM box instead of using these inbuilt capabilities?
Yeah, so I think there are two kinds of answers to that. So in the case, for example, of a small cell that includes GPS inside the small cell itself, that potentially has a lot of cost associated to it because you can have a receiver in the small cell, but you still need to connect it to an antenna. So if you have a small, you have let's say 30 small cells in the building, and you need to connect these small cells to a GPS antenna, you have the deployment CapEx and OpEx costs that I was highlighting in the slide deck before. Even if you have a receiver, you still need GPS antennas. The second aspect also is it's better, for products to be focused and relying on their core function and their core expertise. So a small cell usually has to be placed at a very specific location based on RF reception. The GPS reception might be a completely different location. So we think, and we've been in many trials where operators seem to agree that, small cells need usually, to be deployed in a site survey mode to maximize, the RF. And IGM, for example, can be placed at the best location for GPS reception, and these two might not be the same. And then the other products that you might mention are, the switches, for example, that include grandmaster capabilities. These switches, same thing. The core of these types of boxes are really about switching and routing. So they are not usually experts in timing. And so the timing capabilities are kind of an afterthought. So they might not have the best, capabilities and performance. The oscillator in that box might be mainly meant, for switching reasons and not timing reasons, so might be an issue. And you need to connect that switch anyway to a GPS antenna and the cabling associated to it. So the IGM form factor and the overall architecture of integrating the antenna and the master in the same box is really driven by the deployment costs, right? So you can have some capabilities in another type of box, but you will incur deployment expenses because you will need to connect to a GPS antenna. So that's where we come in. A best of breed timing device that is easy to deploy and doesn't require an external GPS antenna. That's where we come in.
Okay, one more question is around the 1.5 microsecond phase timing spec that you talked about earlier. Do you think that will be tightened in the future, that will need even better performance, or do you think that's likely to be the milestone, the benchmark for some time?
Well, it may be for some time, given that some of the standards are just recently consented and fairly new. But overall, as an industry, and with 5G, there's going to be more and more distributed, smaller, small cells that need to be, where interference mitigation and coordination will be more and more key, as there are more and more devices out there to mitigate. So we believe that because of the multiplication of the number of devices that will be required over time, both for 5G and IoT, the time slot that will be allocated to these devices will become shorter and shorter, so that the spectrum is better used. So because of that, the time slot being more effectively used, it means probably that the requirements are going to be shorter and shorter, and so the requirements are going to be tighter.
All right, and last question then. How phase ready do you think mobile networks are today, just in general, based on these various trials that you've done? And do you notice any variation either by the size of the network, the maturity of the market, or other factors?
Yeah, so in some ways, phase ready, depending on what we mean by that, right? So in terms of readiness, having, the right network elements, having boundary clocks in these elements and so forth, that's something that is fairly, prevalent, in some countries like China, but are more of an issue in other countries where brownfield, investments have been made a few years ago. So the availability of network elements with boundary clocks everywhere is not there today, and that's why J.8275.2 was promoted as part of the standards to make sure that phase can be provided without these types of investments. So now, are all the operators deploying phase today? No. I think It started, in North America, Japan, and Korea, and we see it more and more in Europe. And it's just starting in some other countries, like maybe Latin America is a little bit behind in some countries because they might still be going through the 2G to 3G migration. So it's not everywhere. It's starting, but there are some countries, the advanced countries that are well underway with phase. So there are differences in the regions. But what I wanted to stress is that phase can be provided without having to reinvest, in your network equipment, and that's very important for the operator.
Right. So it's an inevitable direction that the industry is taking. There's 2 or 3 different ways that we can do that, and the products that you've just described are certainly one solution. So thank you very much, Eric. Somebody's just asking if the slides that you showed today will be available, and yes, they'll be posted and uploaded within the next 24 hours. A full recording of this webinar will also be made available, and everybody who's attended will receive an email with links to both of those things. As you can see on your screen now, Eric has published his email address, and feel free to contact him directly if you have any more specific or personal kind of follow-up questions. I'm sure he'd be happy to clarify for you. So with that, I'd like to close the seminar and thank Eric very much for his presentation, and you, the audience, for joining us. I hope you found that useful. Thanks very much.
Thank you, everybody.